So remember last time we finished up with this idea of the winding number. Right. So right, you have some curve, some curve gamma, and you have some point that's not on the curve, right? A point not on gamma, and then we look at this thing, 1 over 2 pi I, 1 over zeta minus p d zeta around gamma. We integrate this guy, and that turned out to give us some integer value, which we called the index or the winding number of gamma around p, right? And this thing, if you actually try to evaluate it, then you get 1 over 2 pi I, 0 to 2 pi, 1 over gamma t minus p, gamma prime t dt. Right. So that's the the concrete thing that you evaluate when you're evaluating the winding number. Okay. And now jumping back to the argument principle, you remember that we had some result like this that said, so we have this thing called the argument principle, which said that again, if you have gamma a simple closed contour, and then f a holomorphic function that was that did not vanish on gamma, right? And so it was holomorphic in some let's say like simply connected domain, and gamma is in that domain. Then if z1 to zk are the zeros of f within gamma, then 1 over 2 pi I f prime over f equaled the sum of all the orders, right? So equaled sum of the ni. So with orders n1 and nk. Then when you integrated this thing, then you got the sum of the orders, right? The sum of the multiplicities. I hope you all remember that. So this was the argument principle, and then if we did this with a meromorphic function, then you would get the sums of the multiplicities of the zeros minus the sums of the multiplicities of the poles, right? Okay. So that's that. But so there's so here's the connection, right? If we consider this thing, 1 over 2 pi I integral over gamma f zeta to zeta, right? And think what is this thing? Well, just concretely, when you spell it out, it's the integral from 0 to 2 pi of f prime gamma t, right, over f of gamma t, and then gamma prime t dt. Right? That's just what it is, of course. Right? But if you think about that just a tiny bit, right, that's this thing here, by the chain rule, is the derivative of the composition, right? So you get f composed with gamma t over f composed with gamma t from 0 to 2 pi, right? Right. And this maybe is starting to look a little bit more like the winding number over there, right? So if I put in a minus 0 here, then what this is the winding number, right? This is the winding number of the curve f composed with gamma, right? It's the winding number of the curve of the image of the curve gamma through f around 0, right? So that's maybe a kind of nicer way of thinking about this argument principle, like a more geometric way of thinking about the argument principle, right? So right. What it says is that, what does the argument principle say? It says that if you have a simple closed contour and you have a bunch of zeros in it, right? You have a bunch of zeros inside you have a function f, right? That has zeros inside of this curve. Then if you look at the image of the curve through f, right? Then the image, so this is gamma, right? And f maps these guys to 0, all of these guys to 0, right? And what it says is that the image of f composed with gamma is going to wind around the origin a number of times that equals to the sum of the multiplicities of the zeros inside. Okay, so that's what the argument principle is saying geometrically. Okay, right, and again, we can say the same thing for meromorphic. If you've got poles on the inside, then that subtracts from the number of times that you wind around, or reverses them. Okay, so that's kind of nice, and I think it's a good way of thinking. So this leads to Rouché's theorem. So if you recall the statement of Rouché's theorem, right? So Rouché's theorem said the following: that if you have f and g that are holomorphic on and within a simple closed contour, gamma, and you had one function was smaller than the other on gamma, right? Then the number of zeros of one guy equals the number of zeros of the sum, right? The number of zeros of the bigger guy within gamma equaled the number of zeros of the sum, right? Right. That is, you could take your function and perturb it by a smaller function, and that wouldn't change the number of zeros. If you allow me to rewrite this a little bit, I'm going to write the condition like this. If you have this and you have another function, so you have another function where the size of one function is greater than the distance between the two functions. Okay. Then the number of zeros of the bigger guy is the same thing as the number of zeros of the smaller guy. Right, so just, yeah. Just rephrasing it slightly. I mean, it's the same statement, of course. Right. Right. This is my f plus g now. Right. This is the sum of these guys. Right. So this is Rouché's theorem, right? Everybody okay? Okay. So this is Rouché's theorem, but now let's think of it in terms of winding. So what is this saying? This is saying that if you have one function which on some curve always attains values that's that the distance of the second guy is always smaller than this guy, then they're going to have the same. They're going to wind about the images are going to wind about the origin the same number of times. Okay, the kind of funny explanation that is given in one book is you want to think of this guy as the owner of a dog, and then G is the dog. Okay, so the owner of the dog is walking around a tree, right? And the length of the leash is shorter than the distance to the tree, right? Because this is f minus 0, right? So this is the distance to the tree. This is the distance to the dog, right? So if the owner walks n times around the tree, the dog must also walk n times around the tree, as long as the leash is short enough, right? Okay, so that's the physical interpretation of Rouché's theorem. Okay. 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 So, yeah. Okay. So let me give a couple more results. Okay. So here's something that is called in one book the n-to-1 lemma. Okay, so this is also pretty useful. So you have some function that's holomorphic on some region omega, and you have some point. You have some point in the region. Okay, and the function is non-constant. Okay. Let n denote the multiplicity of z naught as a zero of a function f of z minus f of z naught. Okay, so you have this z naught is any point. Okay, z naught is any point. You make a function by subtracting off the value of f of z naught. That of course has a zero there, and you look at the multiplicity of that shifted function. Okay, call that multiplicity n. Okay. Okay. Then for sufficiently small epsilon, there exists a delta such that for every point W in the delta neighborhood of f of z naught, excluding f of z naught itself, there exist n distinct points in the punctured epsilon neighborhood that f maps to W. Okay, so, right, so, you know, you have some point z naught, you have f of z naught. Okay, and what this is saying is that, you know, if the order of the zero of the shifted function is n, then you know that there is an epsilon around here. There's an epsilon neighborhood around here. No, you know that for any epsilon, for any sufficiently small epsilon around here, sorry, for any sufficiently small epsilon neighborhood of z naught, there is a delta neighborhood over here that gets a punctured delta neighborhood over here that f maps, that f covers n times. Okay, so f will cover that neighborhood n times. Okay, and of course, this is this immediately gives you the open mapping theorem, right? Because you can see that every point in the image is going to be an interior point, right? Because you can cover an entire neighborhood n times. Yeah? N is one or bigger. Okay, so right, so everything gets every neighborhood gets covered number of times equaling the multiplicity of the zero of the shifted function. Okay, this is a pretty useful theorem, and we've kind of proven it already. The proof of it is hidden in the proof of the open mapping theorem. We just have to sort of refine it slightly. So yeah. So okay. So here's the proof. Okay. So you say, well, look, f is non-constant. Right, f is non-constant, and f of z naught is 0. Right. G of z naught is 0, and this is has to be an isolated 0, right? Because f is not constant, right? So we can choose. So there exists a neighborhood around z naught. There exists a neighborhood around z naught in which g of z is non-zero. In other words, f of z is not f of z naught. Okay, so choose some neighborhood like that. There also exists we can also choose another neighborhood, b epsilon 2 z naught, in which in which f prime is non-zero. Right, because it might be 0 at z naught, but the zeros of f prime have to be isolated, right? If the zeros of f prime aren't isolated, then that tells you that f prime would be constant, right? So you know that the zeros of f prime are isolated, so we can find some neighborhood in which f prime is non-zero, right? Yes? Good. Am I going too fast? I feel like I've lost people. Yeah, no.
Wait, so why does f prime have to be non-constant? Why do you know that our function isn't just like a linear function where f prime would be constant?
We assumed that f was non-constant.
Well, but like f could be non-constant, but it could be like a z plus b, in which case f prime would be constant, but f wouldn't be, right? Oh wait, no, never mind. Then f prime isn't zero.
Yes.
Okay, thank you. Sorry.
That's okay. Yeah. Okay. Okay. Everybody good? Yeah. Okay. So so take epsilon to be the smaller of these two. Okay. So now we have that's going to be our epsilon neighborhood here. Okay. Right. So f of z is not equal to f of z naught, and f prime of z is non-zero in this neighborhood. Okay. So now consider the image of the boundary of that epsilon neighborhood when it's mapped through f. Okay. Okay. Oh, actually, I think I need to put in twos here. So let me do it like this. Okay. I'm gonna say that it's actually the double. The epsilon neighborhood sits inside of the open disk. Okay, so they don't have to worry about being on the boundary. I don't want to be on the boundary. Right? Okay, so I'm going to be entirely inside there. So, right. Okay. So look at the image of the boundary mapped through f, right? We know that that's not going to hit f of z naught, right? So that gives me some something that goes around f of z naught. Right. And let delta be the distance of f of z naught to that mapped boundary. Okay. So yeah. So choose delta. So that delta is smaller than the distance between f of z and f of z naught for all z on the boundary. Okay. So we take some delta that's smaller than the distance to the image of the curve. Okay. Okay. So so now you say, well, look. So now, for any point w naught that sits inside that delta neighborhood, right? Choose any point that's inside that delta neighborhood, right? Well, the distance of that point to f of z naught is smaller than delta, right? Because you're inside the delta neighborhood, right? And delta in turn is smaller than f of z minus f of z naught, the distance of f of z to f of z. So at this point, we pull out the, we use Rouché's theorem, right? We say, well, by Rouché's theorem, the number of zeros of f of z minus f of z naught and f of z minus f of z naught plus f of z naught minus w naught are the same. Right. So that tells you that, right, that f of z minus w naught and f of z minus f of z naught have the same number of zeros, right? Well, f of z minus f of z naught had n zeros, one zero with multiplicity n, but the derivative here is non-zero, so that tells you that the zeros have to be simple, right? So since f prime is non-zero in our neighborhood, right, in our epsilon neighborhood, we know there are n simple ones. Okay, is that all right? Questions? Yeah.
What's a simple zero?
That is that it's not a, it's a zero of multiplicity one.
Okay. Wait, does that say simple ones or simple zeros over there?
Simple ones, simple zeros.
Oh, okay, cool. I was like, what's a simple one?
One in the vernacular.
Got it, okay.
Yeah. One in English, not in mathematics. Yeah. Okay, is that good? Yeah. Okay. 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 Let me do. Right. So, like I said, this n to one lemma, it gives you the open mapping theorem. The open mapping theorem gives you maximum modulus principle, as before. Okay. So here's one more kind of nice consequence of Rouché's theorem. And this is called Hurwitz's theorem. Okay, so here's the statement. So you have a bunch of functions, fn. You have a sequence of functions. That are the holomorphic functions on some region omega. Okay, and suppose that the f sub n converge uniformly to some function f. Okay. So they converge uniformly on the entire region. We know that that gives us that f is going to be holomorphic. Right? So f is thus holomorphic. Suppose that you have uniform convergence to some function, and you have that this function is not identically 0. So f not identically 0. Okay. So if z naught is such that no. This way, sorry. Let z naught be a point in the set, then f of z naught equals 0 if and only if there exist points zn that converging to z naught such that fn zn equals 0 for all n greater than sub n. Okay, so this is kind of interesting, right? It says, like, if these guys converge uniformly to f, and the thing that they're converging to has a 0, well, that can only happen if there's a sequence of points, there's a sequence of zeros for the functions that are converging that are zeros for those functions. Okay, so there's going to be a sequence of points that are zeros for the functions that are converging that converge to the 0 of f. Okay, so let me try to give you some sense of what's going on. So like, so in the real setting, so remark. So it's not true in the real setting. So like, if you consider the functions f sub jx being x squared plus 1 over j, as j ranges from 1 to infinity. Okay, so right, so these guys are just shifted parabolae, right? Right, and none of them have zeros, right? None of them have zeros, but the thing that they're converging to has a 0, right? They converge uniformly to x squared, right? These fj converge uniformly to to x squared, which has a double 0 at 0, right? So they've got no zeros, and then suddenly the thing that they converge to has a 0, right? But so so that that's very different from what Hurwitz is saying. But if we shift to the complex setting, well, each of these guys has 2 zeros, right? Each of these guys has 2 zeros, and those 2 zeros are going to merge together at 0 in the limit, right? So they've got these zeros that converge to in the complex plane that merge back to here, right? Like this. Okay. So that's what Hurwitz's theorem is saying, that you can't have a 0 that just appears out of nowhere. So the proof of this uses Rouché's theorem via a lemma. So, so here we go. If you have f sub n, right, a sequence of holomorphic functions that converge uniformly to some holomorphic function f that's not identically 0. Then, for any closed curve, so any simple closed curve, gamma, inside A. So here's A, and then you have some simple curve gamma inside of it. For any simple closed curve gamma inside of A, that passes through no zeros of f, there exists an n that depends on the curve. Sorry, let me move over here. Okay. So there exists an n dependent on the curve, such that if n is bigger than n, then the number of zeros of fn equals the number of zeros of f. The number of zeros of fn inside the curve equals the number of zeros of f. So this is not this is a, well, anyway. So right, so let me just say it again. You've got a sequence of holomorphic functions that converge uniformly to some function. Okay, these guys converge uniformly to that. And what this is saying is that given any curve, given a simple closed curve, then eventually they're going to have the same number of zeros inside that. They're going to have the same number of zeros inside that curve. Okay. Okay. And the proof is straightforward. You just say, well, look. If you consider the size of f on gamma, right, that has some minimum value. Oops. Yeah. Right. That has some minimum value. Right. Call it m. Right. So you know that this thing is smaller than is bigger than m. Okay. Okay. So further, by uniform convergence, you know that eventually the distance between f sub n and f is going to be smaller than that, right? And then you use Rouché's theorem, right? By Rouché's theorem, you just add them together, and they have the same number of zeros. Okay. So by uniform convergence, right, there exists an n such that as long as you're past that time, then you know the distance between f sub n and f is going to be smaller than that minimum value. But then you have this relationship, right? But then this relationship holds on the curve, and so you know that they have the same number of zeros, and that's exactly what we were saying here. Okay. So by Rouché's theorem.
What is A? Is that just a subset of C?
Oh, I'm sorry, that should have been omega. Yeah.
Don't the integrands converge to each other by uniform convergence? So could we not just conclude that the integrals are?
Well, not so simple, right? Because f sub n converges.
And then because those integrals have to be the integrals have to be like integer multiples of some 2 pi I or something. So then eventually once you have a small enough bound, a large enough n, or is there something wrong with that?
I don't think it's so simple, but it might be. Let me think. I mean, you do have convergence of, I don't think you have automatically, I don't think you have that this will converge uniformly to that, this quotient will converge to that, right?
We have uniform convergence of the numerator and denominator, right?
So, for example, like if I look at, say, f of n equals just 1 over n, right? And
Oh yeah, okay. Because
Right.
because we're talking about zeros.
yeah, right. Like no, I don't think it's I don't think so. What I mean is that, like, if you look at something where the denominator, like so suppose you have something that converges to 0, right? Then things,
Yeah.
it's not so simple.
F is nowhere 0 on the curve though, right? It's just, there might be some sort of problem inside the.
That's true, right? So f doesn't vanish on the curve. So is that okay? Yeah, maybe it is okay. I'm not sure. I'm not sure. Okay. Okay. Let me prove Hurwitz theorem now. So remember what Hurwitz theorem says, that we can always create a if the thing that you converge to has a 0, then we can create a sequence of zeros that converge to that one, for which the sequence is 0 past a certain point, right? Right. F sub n of z sub n is going to be 0 past a certain point. Okay. So here's proof of Hurwitz's theorem. So suppose, and the way that we need to prove is you know, we only need to prove one direction, right? The direction that, you know, if there is such a zero, then we can create our sequence of zeros. So okay, so let's see how this. Give me a second. I kind of forgotten how this goes. Yeah. Okay. So so at this point z0, right? It gets mapped to 0. It gets mapped to 0, right? Again, our function is not identically 0, so so since f is not identically 0, again we can choose some disk around here where the function is non-zero. Okay. So there's some delta such that in the punctured neighborhood, f of z is non-zero. Okay. So we stay away from 0. Okay. And we can assume that it's also on the boundary. Okay. So right. So we're never 0 inside there. Okay. So what's the point? Yeah. Okay. So let gamma sub k be the boundary of the disk of radius delta over k. Okay. So we're just going to take you know, the boundary of the whole disk, the boundary of the half disk, the boundary of the third of the disk, and so on and so forth. Okay. So those are going to be the gammas, gamma 1, gamma 2, etc. So you know, by the lemma that we just showed, we know that we can choose n sub k such that if we're past that point, then the number of zeros of f sub n equals the number of zeros of f. Right. So there's going to be right, if f had a 0 of order m, then a 0 of order m inside there, then we know that, you know, past some point there's going to be you know, zeros. So like if we look at the first disk gamma 1, right? We know that there's some point n1 past which you know, all the f sub n have m zeros, right? So everybody inside here is going to have m zeros inside this first disk, inside gamma 1, right? And we can do that for each of the curves, right? So let's create, we can create an increasing sequence, n1, n2, you know, n3, you know, n4, et cetera, right? So that as long as we're past the first number, then all of the f sub n's have zeros inside of gamma 1. As long as we're past the second number, all of the f sub n's have zeros inside of gamma 2. As long as we're past the third number, all the guys have zeros inside gamma 3, and so on and so forth, right? So just right? That allows us to construct our sequence, right? So just for n in this range, just choose for n in this range. Choose the z sub n where fn zn equals 0. And you notice that the zn all lie inside gamma 1. Right? And you just do that for every range, right? Once you get into this range, you choose the corresponding points. You choose points where these guys will be 0, and those zeros will lie inside of gamma 2, and so on and so forth, right? And so on and so forth, and so we end up with you get a sequence z sub n such that past n1 fn zn is 0 always. Okay. Okay, any questions about that? Okay, so yeah, I'm afraid that's actually all I prepared for today. So that's it. I thought I had prepared enough material to go another 15 minutes, but I'm afraid I ran out. So yeah, that's it for today. Okay. Okay, see you guys next time.
We need that signature by.
What?
We need the signature by.
Bye.
There we go.